Hello, good afternoon, good morning, good evening, whenever you are watching this. So last time we ended by looking at the Euclidean algorithm. So let me go through this again. So what is this? This is a very efficient way of computing the GCD, greatest common divisor of two integers, but it also has many other uses. So to compute the GCD of AB plus many other things, which we will see very soon. Okay, so again, how does this work? The main trick is to use the division algorithm to reduce the computation recursively. So I'm going to show you another example, okay, so which I will reuse in just a sec in a slightly different context. So we're going to compute the GCD of 252 and 198. Okay, so again, I repeat, if you have the prime decomposition of these numbers, then the GCD is easy to compute simply by looking at the primes which appear in both and looking at the exponents. We saw a very nice formula for this, but in general, factoring is not efficient. So if you have very large numbers, factoring is out of the question, but the Euclidean algorithm is very fast. So how does this go again? So we use the division algorithm. So I'm going to divide 250 by 198. So this is 1 times 198 plus 54, right? So I'll call this equation, no, I don't need this right now. I'll do that later. Okay, and I repeat, right? So 198 is equal to 3 times 54 plus 36. Here I'm cheating. I've already computed it, obviously. The repeat, 54. This is 1 times 36 plus 18. And I repeat, 36 is equal to 2 times 18 plus 0. Okay, so you see what I did here is I had my first pair of integers. I wanted to compute the GCD of these two. And we saw the fundamental observation, the fundamental lemma says that the GCD of this pair must be the same as the GCD of this pair. So I repeat the procedure with 198 and 54. Okay. And by exactly the same argument, the GCD of 198 and 54 must be the same as the GCD as 54 and 36. And again, so I divide 54 by 36, and the GCD of 54 and 36 must be the same as the GCD of 36 and 18. I divide 36 by 18, and now I get a remainder of 0, which means I stop, okay? Which means that in my previous pair, in this pair, I should say, then the smaller number divides the bigger number. So the GCD is obviously this number. In other words, it is this number right here. So this is the last non-zero remainder is the GCD you're looking for, okay? So this is it. So GCD of 252, 198 is 18. Okay. Now, the I could write this out to try to formalize this and try to convince you that why it works, right, in a more formal way. But I think that you need only two ideas, and I mentioned this last time. The first is this lemma that I explained in detail, where if you divide using the division algorithm, then the GCD of the first pair is the same as the second pair, right? And so you can just repeat this procedure. Now, why does it stop? It's because in the division algorithm, the remainder is always strictly less. It's always greater or equal to 0, and it is strictly less than the previous value, which means that the remainders must strictly decrease, but they're always greater or equal to 0, so they must eventually reach 0. So this must stop, and you will find the GCD. Okay, so you can't loop forever. So this is a very, very clean algorithm. Okay, so I want now to move on to Bézout's theorem, which is basically the end of section 4.3. I'll have just a few applications of Bézout's theorem, but let me see. Okay, so let's go here. Okay, so Bézout's theorem, I'm going to state it, and it's going to look a bit like, what's that all about? Okay, but it's when I'm going to do applications that you're going to get a feel of for what it means and how powerful it is. So let me state it and then discuss it a little bit. So Bézout's theorem, it's also known as Bézout's lemma. I don't know the history behind this, but here is the statement of Bézout's theorem. So if you take any two positive integers, a and b, okay, then there exist integers s and t, whatever their name is, but we'll use s and t here. So there exist s and t integers such that SA plus TB. So what I'm doing is I'm taking a linear combination of A and B. So it's an integer combination of A and B. And the result will be the GCD of A and B. So this is the statement of Bézout's theorem. Now, if you've never seen this before, which is highly likely, you probably have no idea what this could mean or what's the point and why this should be of interest or exciting, and that's okay, right? So written like that, it's just like, who cares, right? So what? Okay, I will try to show you how important this is. This has many important applications. And we'll see those in just a sec. Okay. So this is a really, really good tool to have. Why is it true? Now, this is a different story. So what's the proof? Okay. There's a short proof, but you'll have guessed it requires induction, so we can't do it before chapter 5. Okay. So short proof uses induction, chapter 5. Okay, so we'll do it at that moment. On the other hand, this proof is a non-constructive proof. Okay, this is a non-constructive proof in the sense that it just shows you that there are S and T that will do the job, but it doesn't tell you what they are. But for us, it is really important to be able to find those S and T. Okay, so for us, for our purposes, it'll be important to be able to compute values S and T. Okay, so we'd like to be able to, I mean, it's really nice that they exist, fine, right? But we need to be able to compute them. So how can we find those values S and T? I can tell you right now from experience that if you try to guess what these values are, it's very unlikely you're going to find them. So if I give you two numbers A and B, and I say find S and T such that the GCD is the combination like that, is just forget it. Okay, so you need to know how to compute this. And the way to do it, very fast way to do it, is using the Euclidean algorithm. Okay, so let's go here. So method, which by the way, is another proof of the existence of S and T. So I'm not going to do a formal proof here, but you'll see how you can compute S and T every time. Okay, so it's backtrack the Euclidean algorithm. Okay, so this is the way to find S and T. So what I'm going to do is I'm going to take my last example, and I'm going to compute the S and T for that. Okay, so to illustrate, last example. So we found that GCD of 252 and 198 is 18. We compute integers S and T such that S times 252 plus T times 198 is 18. Okay, so that's what I'm going to do. I'm going to show you how you can compute the S and T, and the method is important. Like I said, for some of the stuff we're going to do later on, it's important to be able to compute S and T, but it's not difficult. Okay, so if you understand the Euclidean algorithm, you'll see this is not difficult. Okay, so again, Bézout's theorem. You have two numbers A and B. You have their GCD. There are two coefficients that you can find. There's not only one solution. There are many others, but there's at least one solution, S and T, such that the combination of A and B will give you the GCD. Okay, so let's compute this using the Euclidean algorithm. So I'm going to be very, very lazy here, and I'm going to copy paste. Let's do that. Okay, so I've got this. I'm just going to edit this a little bit. Don't need that. I don't need that. Oops. Okay, so this is my first equation. This is my second equation, third equation. So these are the steps in the Euclidean algorithm to compute the GCD of 252 and 198. Okay, so what I mean by backtrack is this. So look at the, not the last line, but the third equation. If you look at the third, by the way, you're doing linear, and you've probably seen the Gaussian algorithm by this time, and you've used back substitution, right? You've learned how to use back substitution. This looks a lot like that, right? It's a bit similar. Okay, so so look at the third equation. I've got 54 equals to 1 times 36 plus 18. So what I'm looking for, let me rewrite what we want to find. We want to find S and T such that S times 252 plus T times 198 is 18, the GCD, okay? If you look at line 3, we can find such coefficients to express 18 as a combination of 54 and 36, right? And again, remember that in each of these equations, the pair that we're dividing one number by the other, the original GCD is always the same as the GCD of that pair we're looking at in that line. So here 18 is the GCD of 54 and 36, and I get an expression for 18 as a combination of what? This has not been designed for left-handed people. 18, I mean, there's some stuff you can do for left-handers, but not everything. I guess I can just flip the tablet around, but anyway. 18 is 54, which is 1 times 54 plus minus 1, 36. I just solved for 18 in my equation, okay? So you see that 18 is 1 times 54 plus minus 1 times 36. Okay, but what I want is a combination of 252 and 198. So what do? Look at the second equation, go up 1, and you see that you can express 36 as a combination of 198 and 54, right, by the second equation. So I'm going to replace 36 in my equation here using 2. So now we use 2 to replace the smallest, which is 36. Okay, so I'm going to get 18 equals 1 times 54 plus minus 1. Okay, so now 36, if you look at the second equation, 36 is 198 minus 3 times 54. 198. And I'm going to, just to make sure that you see the numbers I'm interested in as if they were vectors in a linear combination and the coefficients that we're looking for. So 198 plus minus 3 times 54. Okay, so now I'm going to put the 54s together and the 198s together. There's only one. So I get that 18 is 1 times 50. No. I've got 154. I've got minus 1 times minus 3, which is 3. So that's a total of 4 times 54 plus minus 1 times 198. Okay, so I'm combining these guys to give this, right? Hopefully that makes sense. Okay, so 18 is 4 times 54 plus minus 1, 198. Okay, that's using equation 2. And now I'm going to use 1 to replace So now I want to replace the smallest one, which is 54. Okay, so 18 is 4 times, and now I replace this 54 using first equation. What is 54? It is 252 minus 198, or if you want plus minus 1 times 198. Again, I'm making sure that we see exactly where the coefficients are and so on, plus minus 1 times 198. Okay, and so now I'm going to, I've got what I want. So 18 is 4 times 252. That's minus 4 times 198 and another minus 1, 198. So that's minus 5. So we've got our S and T. Okay. So hopefully you can see exactly how this works. So just try a few of them by yourselves, right? And again, this is also very efficient because the algorithm is efficient. You can just backtrack easily. Okay, it's very simple. Okay, as long as you understand the principle, this is fairly simple. Okay, so again, what does this do? If you're given two positive integers, you can find coefficients to combine them to express the GCD. Okay, now I haven't told you why this would be of any interest at all. Okay, and let me try to do that now. Okay, so this is the way that we can find those. That's an explicit way of finding the coefficients, but there's also theoretical applications of just the existence of these two integers. Okay, so some applications of Bézout's theorem. Okay, so the first result I'm going to show you is really the key thing. I'm going to prove that using Bézout, and then I'm going to prove a lot of stuff with it. Okay, so our first lemma. This is like, really, if you want to understand one thing, just that's the one. Okay, so the key point is this: is that if you take three positive integers and the GCD of A and B is 1. Okay, so I'm going to take three positive integers, and two of those numbers, A and B, have no common divisor bigger than 1. Okay, they're relatively prime, they're coprime. Okay, so if A divides B times C, then A divides C. Okay, so A and B have no common divisors, which means that if A is dividing a product of B with C, then actually A has to divide C completely. Okay, this might be intuitively plausible to you. Okay, but proving this without Bézout's theorem is you can use the fundamental theorem of arithmetic, but it's not very elegant. But with Bézout's theorem, it's very nice. So here's the proof of this. And this is a proof which is good because, one, it shows you how to use Bézout, which is used in many, many other places. Two, because it actually explains, in a sense, why this is true. And it makes you practice playing with all these things, okay? So let's do this. So the big hint here is this. So, GCD of A and B is 1. Bézout's theorem, what does it say? It says this. So Bézout, right, means that there exists two integers, S and T, such that S times A plus T times B is 1, right? Because that's the GCD right there. Okay, so the GCD is 1. So there's an integer linear combination of A and B that gives you 1. Okay, so what do I do with that? I'd like to show that if A divides B times C, then it must divide C. So here's a nice little trick. Multiply, let's call this star, multiply star by C both sides. So you want to get C involved in this, right? So here's what we're going to get. We're going to get SAC plus TBC equals to C. Okay. I'd like to now, what I want to show is that A divides C. Now, C is the right-hand side. If I can show that A divides the left-hand side, I'm done. Half the work is done because SAC, A is a factor, it divides SAC. What about TBC? That's my hypothesis. A divides B times C, so I'm done. Okay, So notice A divides SAC. This is obvious. And A divides T times BC. That's our hypothesis. So A divides SAC plus TBC, which happens to be C. So that's it. Okay. So because I can express one, and this is going to come back quite often, because I can express one as a combination of A and B, things will happen here. Okay. So Bézout is giving me this expression. Notice that I don't need to know what S and T are. I only need Bézout. I don't need to compute S and T. As long as they exist, I can just use them and that's it. Okay. Here is a consequence of this, which is, I mean, we could go on for a long time on this, but it's an alternative definition of what a prime number is. And it's a consequence of this lemma. Okay, let's go here. Okay, so here's a consequence, and yeah. In my notes, it's written as a lemma, so I guess maybe that's the way it's stated in the book. So I'm going to stick to that. I might say corollary. I've never known how to pronounce that word. Corollary, I don't know. Okay, so this is let me write it here. So alternative definition of prime number. So it's a different looking property, but it turns out that it defines exactly the prime numbers. Okay, so a positive integer, I'm going to call it P, hopefully. Be careful with that, okay? It's not because I call a number P that it's prime. It's just a name, right? I could have called it Bob. So I'm using P here because in one of the directions is going to be a prime, but it doesn't make any difference, right? But make sure you don't assign meaning to the letter, okay? So a positive integer P bigger than 1 is prime if and only if, right? So you see that this is an equivalent statement, right? P, the number is prime if and only if it satisfies the following property. So if and only if it satisfies the following. For every AB integers, if P divides the product AB, then it divides one of the factors. P divides A or P divides B. This is equivalent to saying that a number has only two two divisors, which are one in itself, or no proper divisor other than one. So this is completely equivalent, and I'm going to show this. This is going to take a little, yeah. So let's do the proof on the other page. Okay. Actually, I'm going to start because there are two directions, and they're different. Okay. So one direction says if I have a prime, then it must satisfy this condition, and if a number satisfies this condition, it must be a prime. Okay. One direction I could leave as an exercise, but I'd have to tell you which direction that would help. It is the following. Yeah, brain cramp. This way. Let's start with this. I think so. Yes. Okay. So I want to show that if P satisfies this condition, it must be a prime. I'm going to use the contrapositive. So I'm going this way. So the contrapositive negate both, go the other way, right? So in other words, I'm going to show that if P is composite so not prime, then this condition is not satisfied. What does it mean that this condition is not satisfied? It means it is not true that whenever it divides a product, it divides one of the factors. So it means that there exists a product that P divides and P does not divide any of the factors. Then there exists AB such that P divides AB, but P does not divide A and P does not divide B. Okay, so that's what I want to show. Now, if you stare at this for a minute or less, but concentrating, I'm sure you can figure it out. And since I don't know when you're watching this, I'm not gonna, you can just pause for a minute, think about it, but here's the answer. So here's just an example before I show you that proof. Okay, so if P is composite, P divides some product and P doesn't divide any of the factors. But okay, let me just write this. 12 equals to 3 times 4. Okay, so 12 divides 3 times 4, but 12 does not divide, obviously, 3, and 12 does not divide 4, of course. It's too big, right? So if you understand, I mean, this is an obvious statement, right? This is clear. So 12 not being prime can be written as the product of two numbers which are smaller than 12, both of them. And so 12 divides this product. It's actually equal to that product, but it can't divide any of them because they're too small. And that's true for any composite number. So in general, again, this is not a proof, right? But it's the idea of the proof. So in general, if P is composite, then there exists A and B such that P equals AB and A and B are less than P. That's all I need, right? They're bigger than 1, but I don't care. Okay. And so P divides A times B. It's equal, so it actually divides. But P cannot divide A and P cannot divide B. They're too small. P is bigger. So that's it. Okay. So you understand the example. You can extract the general case from the example, which is legit, right? I mean, whatever. I mean, it's as written, that is not a proof, but the whole idea of the proof is in that example. So then you write up the general proof. Okay. So that was the easy direction, as long as you know which direction is easy and how to state it, right? Using the contrapositive. So now I want to show the other direction. I want to show that if P is a prime, then it must satisfy this condition. Now, if you look at this, it looks a lot like the lemma we had earlier. I'm scrolling and you don't know where I'm going. So let me just, let's go here. Okay. So the other direction is this. So to prove that if P is prime and P divides A times B, any A times B, then P divides A or P divides B. So that's what I want to do. Yeah. Okay. So any prime which divides a product must divide one of the factors. I want to prove that. What was that lemma? That lemma said that if the GCD, I see the, okay, so yeah, we have to, okay, I'm going to change the letters completely. If the GCD of big A, big B is 1, and A divides B times C, then A divides C. right? I don't get confused with these A's and B's are not there, and I'm not going to use them in the same context, okay? So if the GCD of two numbers is 1, and one divides a product which involves the other number, then it's irrelevant. It just doesn't count. It actually means that the number divided the other, okay? So look, I've got a prime P that divides A times B, and I want to conclude that it divides one of the factors. And look at the lemma, it's very similar. So, but how do you put them together? Okay. So suppose P divides A times B. I want to show that it divides either A or B. I'm going to split it up into two cases. Case one. I know this looks silly, but so case one, P divides A. Then we're done, right? So case two, don't put P divides B. That's not the second case, right? P does not divide A, right? So it's either one or the other, right? So what do I want to show in this case is that P divides B, right? So to show P divides B, okay? Now, P doesn't divide A. I'd like to get that lemma involved. So I need something with a GCD. And look, A divides big B times big C. And I want to conclude that big A divides big C, right? You can see the pattern here. So basically what I want is, in my context, big C will be little b, right? And big A, big B are P and A, little a. So I want the GCD of little p and little a to be 1. Why is that true? Well, the GCD of p and a is 1. Why? Because, well, p has only two divisors, positive divisors, 1 and p. But p doesn't divide a, so it can't be the GCD, so that leaves only 1. Since 1 and p, the only positive divisors of p, and p does not divide a. So the common divisors have to be either 1 or p, but p isn't, so it's 1. Okay? So the lemma, so using the lemma here, okay, GCD of P and A is 1. And P divides AB. If you apply the lemma, it says that P must divide the other guy. And we're done. Okay. So again, if you haven't, I mean, you can pause now, but at any point, anytime. But work it out by yourselves. Try to follow all the steps, and I think you'll be okay. All right. So, all right. So what have we proved? We've proved that a number is prime exactly when it has this property that when it divides a product, it has to divide one of the factors. So while we're here, I'm going to state a more general version of this, which will be helpful. Okay, but there's nothing new. You should believe this if you believe the previous one. Okay, so if I'm going to call this a whatever. If P is prime and P divides not only a product of two things, but of a whole bunch of things. So let's say the product I equals 1 to n, because we've got this fancy notation, you might as well use it. It looks real smart. So P divides the product of A1, A2 right up to AN. Then it has to divide one of these numbers AI. So then if P is prime in this, then there exists an I such that P divides AI. So we've proved it for n equals to 2, but it's true for any n, or any number of integers. These are all integers. Okay. The proof induction, chapter 5. But I'm going to show you for 3, and you'll see why this has to be true, right? So induction is just a formal process to prove the obvious thing that I'm going to show you here. So let's say I look at n equals to 3. So say P divides A times B times C. Rather than calling them A1, A2, A3, I call them ABC, okay? So if you look at older math books, really older math books, they didn't always use indexing. This indexing is, you know, A1, A2, AN, like that. That's the standard way to write it right now. But they would often use a more informal way, and they would say, let's say A, B, C, 3 dots right up to Z, which seems to say that there are only 26 terms in the C. But they would, I mean, you see that in older books. It's kind of cool. But in any case, if we don't have too many, we'll obviously try to simplify the notation. So P divides A times B times C, and I'd like to show that P divides A, or P divides B, or P divides C, that it must divide one of these guys, okay? We know it works for 2. So what do? Well, P divides ABC. That means that P divides AB times C. So by the lemma, it must divide AB or C. Right? And then you use the lemma a second time. P divides A or P divides B. So one of these 3 cases must occur. And you see for 4 how it works, and 5 and 6. So you see the pattern. Induction is the formal way to say it's going to work for any n. Okay. Okay. But you see, once you have it for 2, obviously it works for any number of factors. How are we doing all the time? I have no idea because I didn't pay attention. Very smart. Okay, last thing I want to do. I don't know if I've discussed this earlier, but let me go back to ZM. Remember that we have a sum and a product, which behave very much like plus and product in Z, right? So they're associative, commutative, you have the distributive law, everything works exactly the same as in Z, but there is one difference. And it's an important difference. We know the following is true in Z. So this is true for the integers. Suppose that A times C is equal to B times C. Now you're tempted to say, yeah, then A is equal to B. Maybe not. There's one exception, right? If C is 0, then you can't conclude that A equals to B, obviously, because you can choose any A and B you want. If you multiply by 0, you just absorb everything. But if C is not 0, then it is true that you can cancel out and A equals to B. Okay. Okay, so this is true in the integers. It is not true in general in Zm, but this is not true in Zm in general. I mean, it's true for certain values of m, and we'll get to that. But here's an example. Yeah, let me, yeah, why, what the hell? 14, yeah, that's 2 times 6, 7. I'm looking m equals to 6 here. 2 times 7 is 14. This turns out to be the same as 2 times 4 in Z6. Okay? That's stupid. Okay, I should just cut the video and edit it out. Let me not write that this way. I'm trying to do something differently from my notes, and it's a big fail. Okay. 7 is not in Z6, so that doesn't work. Okay. Another way of saying this, I have no choice. Okay, so in Zm, right, when we multiply, we mod out to get the value. So what I'm saying is this. So it is not true. I'm going to leave this in. I'm an honest guy. Although I'm tempted to cut it out, you'll never know. It is not true that AC congruent to BC mod M implies A congruent to B mod M with C not equal to 0. Even if C is not equal to 0, it is not true. This is not true. Okay, this is exactly the same statement that I was making for about Zm, right? Because that's what I wanted to avoid. But anyway, A times C and B times C, if you compute them in Zm, they're equal if they're congruent mod M. But okay. Damn. Okay, so here's my example. Now it makes sense. If you look at 14, it is congruent to 8 mod 6. Both are the same as 2 mod 6, right? This is clear. But if I divide by 2, right? So this is 2 times 4 congruent to 2 times 4. 2 times 7 is congruent to 2 times 4 mod 6, right? But 7 is not congruent to 4 mod 6. One of them is 1 mod 6, the other is 4. Okay, cannot cancel out 2. Okay, and this is really annoying, right? We're used to Z and doing that without thinking, but when you're working in Zm, this is not going to work out so well. So you have to be extremely careful. But maybe you can see why. I mean, there's a connection here that 2 and 6 have a common divisor, which is 2, and that's the key point. Okay, so the reason, I'm rambling, sorry. So the reason is that the GCD of 2 and 6, this is our C and our M, is not 1. That's the reason. Okay, so you can sort of absorb things in a strange way. But if the GCD is 1, you can cancel out. Okay, so that's the key point, and I want to show you. And this is again Bézout, but otherwise we're fine. And this is going to be extremely important in what follows in 4.4, which is extremely important for RSA cryptography. Okay, otherwise we are okay. So lemma, so theorem. This one gets the name of theorem in the book. It's theorem 7 in the book. Okay, so I have my modulus m, some positive integer, and I have 3 integers a, b, c. Okay, and suppose that the GCD of c and m is 1. Okay, then it is true that you can cancel out c in any equation. Then AC congruent, I mean equivalence mod m, AC congruent to BC mod m implies A is congruent to B mod m. Okay, so if you look at this, this is just the same as is in Z, right? AC equals to BC, I can cancel out the C, but the condition is different. In Z, just all we need is that C is not 0. But here we need something stronger. We need that C and M have no common divisors greater than 1. Okay, so let's prove this. It's easy. It's easy if you know what you're doing, obviously, which is yeah. But I mean, there's no tricky things. I mean, we've developed everything we need to do it, and it's short. Okay, so AC congruent to BC mod M means what? By definition, it means M divides the difference, right? M divides AC minus BC. Okay. So M divides A minus B times C. Now that first lemma we saw, it says if a number divides a product and it is relatively prime to one of the factors, then it divides the other guy, which is exactly what we want here. So first lemma says, no, I don't want to say that. By our first lemma today, I should have given it a number. GCD of MC equals to 1 implies M divides A minus B. And what does that mean? It means A is congruent to B mod M. Oh, I hope this makes sense. Okay, so it is really that first lemma that we saw. If a number divides a product and it is relatively prime to one of those two numbers, then it means it had to divide the other guy. There's no contribution from the relatively prime number, relatively prime, yeah, in this division. Okay, so and this is exactly what I'm using. I could have done this theorem right after that lemma. It's just basically just that I'm applying the lemma directly, nothing else. Okay. Now, notice what this means. It means that in Zm, the numbers in there which are relatively prime to M, you can always cancel them out. They're invertible. This is fundamental. And so in particular, if M is prime, then all the numbers in Zm except 0 will be invertible, cancelable, which makes Zm, when M is prime, a very, very nice structure, even nicer than Z. It's actually more like the rationals or the reals. It's a field. So the non-zero elements are invertible. They have an inverse. I'm lying. I should add one little thing here. You have to use Bézout for that. I'm sorry. Anyway. Teaching without an audience is difficult. Okay, so I've got my theorem, and yeah. What I meant is that yes, the numbers which are relatively prime to m are invertible, and in primes are all invertible, but it's not quite what I'm saying here. What I'm saying here is a bit weaker. It's just that they're cancelable. But with Bézout, you can actually find an inverse in Zm. That's a different thing. Look at the exercises. We'll discuss this next week. This is it for today. I think so, yes. And I'm done with 4.3. This is the end of 4.3. Please do exercises. It's important. The test is coming up in pretty quickly. I'll tell you next week. Exactly. Okay, so that's it for today. And I'll see you next time. If you have questions, just send me a message. Cheers.